Hello, everyone. My name is Jakub Chojnacki, and today I would like to talk to you about the reinforcement learning library called Ray RLlib, and why do I think you should care about it too. My main goal for that presentation is to basically convince you to try this framework yourself. And to do so, I've divided this presentation into 3 sections. So first, I would like to answer why, in the first place, should you use Ray RLlib. In the second part, I would like to answer the question how, if so, should you use the RLlib. And after that, I would like to show a few examples of what can be achieved with that package. Okay, so let's start with why. So before we answer the why, I would like to make a brief recap of reinforcement learning, so to ensure that we are all in the same page. Basically, I'm aware that most of you have seen this image already many times, but I would like to reiterate that in reinforcement learning, we have basically 2 components. There is an agent that is basically a sole decision maker, and the environment. And you can think of the environment as the problem description. And the agent is the solver to that problem. And basically, the role of your agent is to predict or compute such actions that, when fed to the environment, will invoke such a transition that will end up with the environment giving you the highest possible rewards, such that you will optimize your objective function. So maybe you would like to maximize the score on your Atari game. Maybe you would minimize the number of crashes of your autonomous vehicle and whatnot. So agent is interacting with the environment in order to solve the objective problem in the environment via action prediction. So you can think of the reinforcement learning framework, like any framework, into 3 parts. So at first, basically, you have to interact. And by interact, it means that each agent that you have, it will employ its policy to interact with the environment, and it will collect some data through the actions. So this is the interaction part. Then every agent will evaluate its performance. So given you've collected via the agent and its actions some set of data, it can be the framework such as Markov decision process or partial observable Markov decision process or any kind of stochastic game process. It doesn't matter. It basically means that your agent has collected some batch of data. And after that, your system, your agent, would like to improve itself. So again, since we've been using some policy to gather the data, now we would like to improve based on the evaluation. So if our agent basically computed that certain actions are bad and certain actions are good, given concrete policy, we would like to do more of the correct actions and less of the bad actions. And this cycle will continue until we reach optimal policy, so the optimal behavior of our agent. And to further explore this topic, I would like to bring the quote from George Hotz, which basically says that, well, in supervised learning, the weights depend on the data, but in reinforcement learning, the data depends on the weights, and the weights depend on the data. So we have a cycle there, because if you think of it, your policy is underneath most likely some neural network, right? And so when your agent is interacting with the environment and gathering the data, it's gathering the data using some weights via your neural network. And later, the data gathered by this policy is updated given the data that you have gathered. So we have a cycle there, and this is basically one big thing that leads that the RL is hard in principle. And so given that we have this circular dependency on weights and data, there are a few issues with RL that makes it hard. And so For instance, many of deep RL algorithms are very sample inefficient, so you may need multiple interactions with your environment and thus millions of your data samples. Also, in most of the real-world environments, your state and action spaces are huge. For instance, in StarCraft 2, the state space has more possibilities than there is atoms in the observable universe. And also, most of deep RL algorithms are super sensitive to hyperparameters. So on the right, you can see a few algorithms performing basically on a Atari game, and you can see that there are like super big differences between the algorithms. And fun fact is that most of them are just DQNs or some variations of DQNs with different hyperparameters and different neural networks and approaches. So it's super sensitive and super hard to tune your hyperparameters for any RL problem. And then, of course, comes things like, it's pretty hard to determine which action led to eventual rewards. So we have the temporal credit assignment problem. And on top of that, there are also those multi-agent settings at which, there are many agents and your environment becomes thus non-stationary, means that not only a single agent is making changes in the environment, but there are many agents interacting with the environments, making changes, and thus, from a perspective of a single agent, the environment is non-stationary, making it even harder. And to be very concrete, I would like to present to you some example, which is a StarCraft multi-agent challenge called SMAC in short. And this is a challenge that presents basically all of the problems. So it's a simplified version of StarCraft 2 solved by DeepMind. It is a pretty known benchmark for multi-agent RL. And it's basically focused on controlling a group of units, which is called microing. And basically, whoever controls those units better would win. So the problem objective is rather simple. So you would like to, given your group of agents, defeat the other agents with basically taking minimal damage. And so our role as a developers is to train the system to micro every unit such that it would defeat the insane computer, which is the hardest computer in StarCraft 2. And so at each state, you would want to choose the best action for each unit in order to solve that problem. And so, for instance, you can see that some environment like MMM2 basically presents to us two groups of units, which are Medivacs, Modulars, and Marines. For those who know StarCraft 2, you can already know that this is hard to micro example. And basically, each unit is controlled on itself by the RL agent, and our role is basically to teach the agents such behavior to defeat the insane computer with the same but outnumbered unit count. And so, what would be the intuition if you would like to solve such a challenging problem? So at each game frame, or we can call for it a state or observation, we would like to select an agent from our control group. We would then observe the current situation from the perspective of that agent, and we would determine some actions for that agent, given its policy. Then we would execute that action selected by the agent. So for instance, we would attack some other unit, and then we would move to the next agent from our control group. And we would repeat the steps 2 to 3. And of course, we would play until we find the right action per agent per state, meaning that our policy at some point for all the agents would converge to the optimal one, meaning we would win every time. And so, given that example, why still would you care about any framework? If we know the mental idea, where is the problem? Why Ray RLlib? So, first and foremost, every multi-agent system requires many interactions with the environment, and having a single environment is pretty hard for any RL problem. So RLlib is able to simulate many environments and many agents in parallel with fault tolerance, meaning that there is a high possibility that if some environment collapses or has some exception, there is a time window at which it will be responded by the Ray RLlib. Second of all, there are plenty of RL algorithms. So for instance, you might try with some simple algorithm like proximal policy optimization, PPO for short, but at some point it might do well with simple scenarios like few marines against few marines, but in more challenging environments, maybe you would need some model-based approach like Dreamer v3. And you have those algorithms out of the box. You can just connect to those and try on your machine. The second part is that, well, you can basically seamlessly scale from laptop to GPU. So it's pretty common to start with your, laptop, try to solve some simple issue. And when you hit a wall with your laptop, you basically transfer to some GPU cluster and maybe some more demanding algorithms or maybe some more demanding environments or more agents and more environments. Second, and the part to that is that also you are allowed to have modular architectures, so you can mix any RL paradigm. So you can have multi-agents, you can have model-based, you can have on and off policy models. So it's everything configurable. So you can have your basically PPO with a multi-agent settings. Pretty simple to do. And of course, it's self-hosted and cloud. So you can start, simple on your machine. And again, if you hit a wall with your compute, you can pretty simply boot your Docker and connect to any kind of cloud. Okay, so how do you use this package then? So first, let's basically have a mental image of exactly what it is. So Ray RLlib is a part of a bigger ecosystem called Ray. And Ray basically is a package that allows you to make a distributed training of any kind of machine learning workload. So for instance, given that we've got this RLlib that is able to spawn any kind of pre-trained RL algorithm and some environment, we can also have some kind of package that allows us to serve. So for instance, we can deploy our model to some endpoint and use some sophisticated techniques to inject it with some more data. We have some tune options, so we can optimize our hyperparameters with many grid searches, Bayesian optimizations, and PBTs. These are pre-built. Of course, we can train our machine learning workload, and we can have a pretty strong and effective handler for large-scale data sets that basically are pretty important for any kind of behavioral cloning or any kind of RL that is basically in an offline setting. And to top that with more information, we can also pretty easily scale with any scale, because any scale is basically an owner of Ray RLlib. So if at any point, for instance, you would also need, maybe some large language model or any kind of cloud compute, it's pre-built in the any scale. So you are welcome to use the cloud possibilities with the Ray RLlib and any scale. Okay, so now how do I use it then? Let's answer this question. So as with every reinforcement learning problem, we have to start with creating our environments, our problem. So for instance, you can use any kind of available environment creators like Gym or nowadays Gymnasium, or for instance, Unity. It's up to you. Next, this is the most important part of your Ray RLlib integration. You have to create a configuration. And you should think of the config file as your command center. This will be your entry point to your algorithm config, and this will be the entry point to the entire Ray RLlib. After you create this configuration, your job is to register your created environment in this config. Also, you can then register your devices. So you can say that you would like to use your GPU and CPU and whatnot. And after that, you are ready to go. And so the thing that I really find pretty important in any RL is that every time you should first tune your hyperparameters. And this is why the Ray tune is pre-built into this entire ecosystem. And trust me, this will save you a lot of time. It's pretty powerful, and it really helps you find the best, or perhaps good hyperparameters for your RL algorithm. And after that, you are free to go to train and test your tuned agent with Ray Train. And so how does it look like? So first of all, let's start with the environment. So let's say that we have created a gym compatible environment. So we have defined the reset function, which will return some starting observation and will reset the environment. We've created the reset, the step function that will basically transition our environment to the next state given the action, and return the observation, action, reward, and so on and so forth to us, and optionally render function. So maybe we would like to see what's going on in our card pool or anything like that. And so the pretty important part in the environment configuration is the observation and action spaces. So we've got basically two possibilities there. So our observation and action space can be, for instance, discrete. So this go left, go right, or throttle, and the values are somewhere in the environment hard coded. So the agent does not have the control over how much can it go left and how much it can go right. Or it can be continuous. So for instance, maybe it would like to throttle 21%, or maybe it would try to stop with having like negative throttle or something like that. So it has control over the amount of the action it can input to the environment. And after that, there's only a single line of the configuration. You can see there's this PPO imported from the algorithms, and this is your algorithm config. And this is where you basically instantiate your algorithm, you prepare your configuration, so you pass your environment, and you are ready to go. But Ray RLlib wouldn't be that awesome without this single feature. So the single feature that is super awesome is the actors. So actors are basically a distributed entities that you can spawn in a centralized or decentralized manner. So you can think of it as, well, if you really need many samples from your environment, then you can have many environment runners. So for instance, given a single policy, you can have 10 actors that would spin 10 environments and would basically play 10 environments and gather the data to you. The second part is learners. So basically you can have 10 learners or 5 learners or as much as you want, and those may have some different optimization strategies for your for instance critic and for your actor, or for your policy and value function, and of course those are connected. So for instance, since your learners and actors are learners and environment runners would reuse some kind of shared policy, you can control how much of the policy update you would like to share between the environment runner and the learner itself. So it's pretty configurable. You may have, as many actors per environment and as per learner, and it really makes the learning way faster, and it scales pretty good with the compute. So if you have like a super powerful GPU, you can spin it to the maximum. And so when you have those actors and you have in those actors basically the learners and the environment runners, first thing that you would like to do is, of course, make the hyperparameters tuning. So again, maybe you would like to have 5 different actors per each, and each actor would have a different hyperparameters for the optimization, and you would like to use some for instance, grid search for those parameters, or maybe you would like to use some population-based search. And thus, you would spin 5 different centralized actors to find the best hyperparameters. And after that, you choose those hyperparameters, you put them into your algorithm config, and you train your agent for as many steps as you want. And so it looks like that basically when you start your training, most likely if you give, the device flag -1, so you say, well, take every resource I have on my computer, then you will most likely watch your new MacBook Pro burn or any other resource you have. But after that, most likely you will have some kind of result and, well, maybe some fun with your trained agent. Okay, so what can be achieved with this library? And so there are plenty of companies that used Ray RLlib and Ray in general, and there are just a few. So JP Morgan, Anybotics, Intel, AI, and Uber had used many different reinforcement learning algorithms. Some of them were model-based, some of them were multi-agents, some inverse, and so on and so forth. But the main point is that every of these companies had huge amount of required interactions with the environment to train their agent, and thus they needed some distributed training in their pipeline. And so basically, just to give you a big picture, in Ray RLlib, you can pretty easily spin your single RL and multi-agent RL algorithms with many environments runners and many learner runners, which are called groups sometimes. And basically, you can configure, any kind of interaction between them. So you can start with single RL PPO, and then in your configuration define, some shared policy for your multi-agent PPO, or maybe you want to have the decentralized QMix like architecture. So you're free to go with your configuration. Everything can be configured in this algorithm config. Same goes with the offline and behavioral cloning. So maybe you've got some pretty good replays of your StarCraft to play, and you would like to first clone the behavior of the human. So again, you can make a pretty simple BC config. You can put the Ray data into it to really nicely sample the data from your video replays, and then you basically sample from those data and have your learner group learn the offline data in your RL settings. And of course, it wouldn't the world wouldn't be that nice if we didn't have model-based RL. So if you like Dreamer v3 like me, of course, you would like to have possibility to not only spin many environments, but you would like to spin many world models. So if you are that lucky and have like pretty good GPU card, then of course you may have 5 environments runners, 5 environments, 5 world models, and 5 learners. And in the distributed settings, everything will work just fine. And hopefully we'll have fun with those model-based approaches that are lately like pretty powerful, and I think might be the next go-to in reinforcement learning. And of course, there are many more. We would need way more time to list all the possibilities with that package, but hopefully at that point, I've convinced you to give it a try and check yourself whether it's something for you, and try to train your RL agents of some awesome environment. So thank you everyone for that. I hope you like the presentation, and see you soon.